Okay, thank you. Well, let's get started with the last part of the day now. We're going to finish talking about Stanford technologies. And what we're going to do now is we're going to have four researchers talk about different technical areas within the GCEP portfolio. They're also going to talk a little bit about what's going on outside of GCEP as well. In the interest of time, what we've decided to do is we're going to have each speaker speak, and then at the end, after all four talks, then we'll have a Q&A session, and then we'll wrap up with two of us talking a little bit about other research outside of GCEP. So let's move right on, and our first speaker is Professor Lynn Orr. He was the first director of GCEP. He's currently the director of the Precourt Institute for Energy, which is a broader group of all the energy research programs at Stanford. And he'll be talking about fossil fuels, carbon mitigation, and advanced combustion.
So I'll try to move things along here. Sally did a very nice job of talking about the reasons why fossil fuels are likely to be part of the energy mix. And maybe I'll spend just a little more time on the shale gas issue, because that's something that came up earlier, and so I don't need to say any more here. Fossil fuels, even if you looked at moving very fast in deploying all the renewables now, just the size of the energy system is such that we're looking at an extended period during which we will make a transition with fossil fuels. And so that just says that we need to be prepared to deal with them even as we work hard to reduce greenhouse gas emissions. So if you think about the ways to do this, there are really kind of three ways that you can make fossil fuels reduce their greenhouse gas emissions. One is to improve combustion efficiency. And really we should do that at every opportunity, because combustion efficiency is the primary way we turn fossil fuels into some sort of energy service. And to the extent that we can make that more efficient, then we're obviously better off per unit of energy. We just have less CO2 to capture or to deal with or even to emit. So, but efficiency alone doesn't get us very far down the road, or doesn't get us far enough down the road. So another possibility is to capture and store some of the CO2 in the subsurface. And then finally, we can think about switching fuels to lower carbon content. And the obvious choice there is coal to methane, although coal to solar or wind does even better. So there are lots of opportunities there. So let me just say a few words about each of these. So we humans are pretty inventive. If you look back over the 300 years since the steam engine was invented, the first version of it was about 0.5% efficient. And over the next few hundred years, the efficiencies have gone up. And if you look at the best in class now, the solid oxide fuel cell with a heat recovery gas turbine at the end can get in the neighborhood of 70%. So that's pretty good. In fact, human-engineered systems that kind of do better than about 50% of the theoretical efficiency are actually pretty good. Now, in transportation kinds of settings, we haven't got that far yet. If you look at a typical internal combustion engine, it might do the good ones maybe 25 or 30% in the actual vehicle on the road. So looking for ways to improve that is an important thing. Hybrid technologies certainly go a significant way down the road. But in particular for the long haul, big diesel kinds of transportations, that's a place where having low carbon, low soot, high efficiency engines would be a real breakthrough. So there's a group at Stanford that has worked on this, Chris Edwards and his students. And among other things, what they've tried to do is to look at where does the heat not get converted into energy. And part of it goes as waste heat just from keeping the engine cool enough to operate, and part of it goes out the exhaust stack as hot gases. So you can reduce the fraction of that by pushing the states of that you get to just before combustion to make them to go to much higher compression ratios. Turns out to be the most practical way to do this. Now it requires, of course, changes in materials, and it also requires changes in the way you take the energy out of the engines. But they've managed to demonstrate very high efficiencies in excess of 60% in the single cycle conversion. And a company has now been formed to do this. Now, we heard actually a nice talk earlier about the benefits of reducing soot and black carbon emissions. This is an opportunity to do much better there as well. Sally already mentioned the idea of carbon capture. So the trade-off that you always face in these carbon capture kinds of systems is that you're trying to balance. You'd like some sort of a solvent. The way it's done mostly now in commercial operations is using a solvent, and you'd love to have a solvent that really gloms onto the CO2 very effectively, but then gives it back easily. And those two are very much in conflict. If it really absorbs well and very selectively, then it usually have to put in lots of energy to get it back. So biological systems do this already using carbonic anhydrase kinds of enzymes to do this. And they have the advantage that they're pretty selective. And the energetics of this work pretty well. Now, the concentrations are typically much lower in biological systems, so the challenge is to engineer a setup that will do this and can do it at the kind of scale that we need to do. But it's an opportunity to apply a new set of ideas to a technology that needs to be done if we're going to capture CO2 and store it in a big way. The big cost of CO2 capture and storage is the capture part of it. So then you can think about where to put the CO2. Actually, Mother Nature does this on a very long time scale right now. The way CO2 is removed from the atmosphere in the long term is by weathering of things like silicate rocks. It also happens that you find sometimes massive underground magnesium carbonate kinds of settings, and those are apparently formed naturally. So there's a group that's been busy looking at how do those happen and what kinds of mechanisms there could we possibly use to store CO2 in solid form in the subsurface. Sally also mentioned the idea of supercritical oxidation with water. The idea here is that you would take water, you don't want to use potable surface water, you take salt water out of an underground reservoir, do the supercritical oxidation with water, use a standard heat engine to make power, but then take all the CO2 that goes with that and dissolve it in some more of the brine from the subsurface. So what you put back into the subsurface is an already dissolved CO2 brine, not a separate phase. The advantage of that is that it turns out that CO2, when it's dissolved in water, has a density that's pretty high. So it means you don't have to put as much volume in and you don't have as big a pressure rise in the subsurface. The price of this is a hit on the efficiency of the power plant. So it still costs you energy to be able to do all this. But they've been able to show that somewhere up in the high 30s, say 37%, is a possibility. So let me talk about the another area where there really is actually an economic incentive to put CO2 back in the ground right now, and that's in the area of enhanced oil recovery. This, of course, is not a new idea. It's been worked on even in field-scale commercial activities since the 1970s. And in fact, I started my career as an engineer working on high-pressure CO2. And the good news is that if the pressure is high enough and the oil has the right composition, you can actually move oil very effectively. This picture here is done in a high-pressure experiment in a glass micromodel, but the center part where it's clear, That's oil that was displaced completely by the CO2. There's lots of good mathematical theory involved, and I've spent a whole lot of my career working all that out with a bunch of smart students. The problem is that when you get to field scale, it's actually hard to make the CO2 go where you want it to go. CO2 has very low viscosity, even at very high pressure, so it will find the easy flow paths through the system. So a big part of the challenge of enhanced oil recovery is to figure out how to predict where the CO2 is going to go, and then mitigate the effects of the early breakthrough of injected CO2 when it gets to the other wells. Now, we have had lots of experience at Stanford and a big group of people working on these kinds of things. I'll just give you one quick example of the kind of thing that can happen. We always do use big computer models to predict what happens in the subsurface flows. And when you try to account for the detailed transfers of components between phases, these can be quite time-consuming. So we've cooked up a set of methods that even in relatively small two-dimensional simulations can do things hundreds to thousands of times faster than the conventional ways to simulate these kinds of things. And when you go to 3D simulations, they're really the only feasible technique to do these kinds of things for detailed simulations. We have a number of faculty working on various aspects of flow of CO2 in the subsurface, and it's an area where that expertise can certainly be applied to the CO2 sequestration area. Let me finish by talking about sort of two aspects of substituting natural gas for coal. There are big health benefits and air pollution benefits from doing this substitution. There are reduced mining impacts. And due to the fact that you have less carbon in the fuel per unit of energy, plus the efficiencies of the power plants, in the United States, a typical coal-fired power plant efficiency is 33%. So if you go to 60% in a combined cycle power plant and have lower carbon in the fuel, then you can get 50 to 70% reductions in the amount of CO2 per kilowatt hour of electric power generation, a quite big improvement, provided, of course, that we do a good job of controlling fugitive emissions of methane. Now, I would argue that we actually know how to do that. It's a question of making ourselves pay attention and actually doing the job, but we do know how to do it. So you say, well, okay, fine. Where's all the methane going to come from to do this? And several speakers have mentioned the question of shales. Shales are organic-rich, fine-grained rocks that actually have been treated as source rocks for the natural gas and oil that we do produce. The issue is that they have very low permeability, so the fluids do not flow easily through them. And so the technology revolution has come from the fact that people can now drill very long-reach horizontal wells, and that they can sequentially fracture those so that you create lots of opportunities for the flow into the wells. The shales are widely distributed around the world. Not all shales are created equal, so some have more or less organic content, and some have more or less clay. So there's lots to be learned about shales in various places. India has abundant shales in some places, and so there's a real opportunity here to learn how to apply some of the technology developments in the setting here in India. There's still all the issues of distributing methane if you're going to use it for home heating and cooking and so on. But in any case, even for electric power generation, the possibility is there. But of course, there are also lots and lots of interesting questions about how all this works. One of the things that's a little surprising about all this is that the shale wells, they often produce very fast, decline pretty fast, but then show a pretty long tail. And it's that tail that is puzzling because it actually looks better than it should be based on the simple a simple picture of adsorption and diffusion. So understanding how these things work as for the different kinds of shales is something that's underway now. We need to understand better how they fracture these rocks. They show big differences in their strengths depending on how much clay is there. It turns out that most shales will store more adsorbed CO2 than they do methane. So there's at least the possibility of replacing some of that methane with adsorbed CO2 as a way to both recover the methane and reduce the emissions of CO2. And of course, we'd like to be able to get the economics right, so that means working on the long-term modeling. And finally, having natural gas available to help us deal with the question of firming intermittent renewables like wind and solar offers some more opportunities for a combined energy system that can integrate large quantities of renewables in an effective way. So I'll finish here and just say that Sally said this already, there's plenty of fossil fuels out there, so reducing worldwide greenhouse gas emissions is going to require us to use them in a very different way in the future than we have in the past. Substituting natural gas for coal and electric power generation reduces CO2 emissions and has lots of other benefits as well, so we should take advantage of both of those. It's also true that if we're going to capture CO2, we can do that from a natural gas combustion product stream just as well as we can with coal. In fact, in some ways it's better because there's a lot of other stuff in the combustion products from coal. So that offsets the fact that you have to handle more gas. And then shale gas, of course, has the potential for significant additional supplies worldwide with good research questions that can be pursued in the Indian context. And then finally, capturing and storing CO2 in the subsurface can contribute significantly to emissions reductions, and at least initially, enhanced oil recovery can help pay the bill for some of that, even as we work on the other kinds of things. Thank you very much.